Question 6. The second step in the maintenance of sulfuric acid is the conversion of SO2 into sulfur trioxide SO3 using equilibrium 1. You can see there 2SO2 plus O2 gives 2SO3. An industrial chemist carries out some research into equilibrium 1. The chemist fills 10.2 decimeter cube container with SO2 at room temperature and pressure, then adds 12 grams of oxygen. The chemist adds vanadium 5 oxide catalyst and heats the mixture. The mixture is allowed to reach equilibrium at a pressure of 2.5 atmospheres and a temperature of 1000 Kelvin. A sample of the equilibrium mixture is analysed and found to contain 0.35 moles of SO3, and we've got to write the expression and then calculate Kp. So we're looking at Kp. Now, marking a significant quantity of the papers, very, very large amounts of you have written expressions for Kc rather than Kp, and therefore you did not get the marks. Kp refers to the partial pressures of the species in the equilibrium, not the concentrations. So anything written with square brackets is immediately going to lose a mark. So Kp equals the partial pressure of SO3 over the partial pressures of SO2 and O2. So we're going to have P to represent the partial pressure, round brackets, SO3 squared, divided by P, round bracket, SO2 squared. Remember, the powers are because of the balancing in the equation, multiplied by the partial pressure of the oxygen. But your brackets must be round. Now, units, we're dealing with pressure, not concentration. So many of you wrote units for moles per decimeter cubed. We haven't got that. We've got pressure. We're told it's 2.5 atmospheres. So your units are in atmospheres. We've got atmosphere times by atmosphere on the top. On the bottom, I've got atmospheres times by atmospheres times by atmospheres. It's 3, 2 and 1. So they cancel, leaving me with 1 over atmospheres. So that therefore is ATM to the minus 1. Okay, so 1 mark for the expression, 1 mark for the units. Now let's look at the calculation. Determine the value of Kp for equilibrium 1 at 1000 Kelvin. Show all your working and give your answer to 3 significant figures. So like a previous question, we've got a certain number of sig figs to give our answer to. Try and keep the Kp expression in shot when we do the calculation, but let's look back at the information we've been given. What do we know? If I'm working out Kp, what I need to know are the amounts at equilibrium of all 3 species in my equation. I need to know the total number of moles that are involved. I need to know the partial pressures. So whenever you're dealing with any Kp or Kc calculation, you need to draw your table, your Rice table, how we taught it to you in your lessons. So let's put the equation in. I've got SO2 plus O2 giving me SO3. 2 of those, 2 of those. Remember then your table is R for ratio, I for initial concentrations, C for change in concentration or changes, or so initial amounts and change in amounts, we're not dealing with concentration, E for the amount at equilibrium. Okay, and then with Kp, with these ones we want X for your mole fraction, and then P for your partial pressure. So it's the Rice-Exp type table for this one. So start with R for ratio. 2 to 1 to 2. I, initial amounts, the initial amounts of the chemicals. So go back to your question. What do we see? We've got 10.2 decimeters cubed of SO2 and 12 grams of oxygen. So obviously my initial amount of the SO3 is going to be 0. Now I cannot just go, 10.2 and 12. The initial amounts are the initial number of moles. I've got a volume for my gas at RTP. I've got a mass for my oxygen. So I can work out moles of each of these separately. So let's do that to the side. First of all, my moles of SO2. Moles of a gas at room temperature and pressure is equal to volume divided by 24 or 24,000. Remember, 1 mole of a gas occupies 24 decimeters cubed at room temperature and pressure. So if I've got 10.2 in decimeters cubed, I'm going to divide that by 24. That gives me my volume of 0.425. So my moles of 0.425. So that's my initial number of moles of the SO2. Same thing now for the oxygen. I've got 12 grams. I've got a mass of oxygen. So my moles of O2 is mass over molar mass. 12 divided by 32. Oxygen is 16. O2, therefore, is 32. Now, from the class that I marked, many of you put 16 there. Very, very silly mistake. 12 over 32 is 0.375. Let's put that into my table. Okay, I need to now figure out how much these change by, and that will be related to the ratios in the equation. Let's go back to my information. The chemist adds the vanadium oxide catalyst and heats the mixture. The mixture is allowed to reach equilibrium at a pressure of 2.5 atmospheres, and a sample of the equilibrium mixture is analysed, and it was found to contain 0.35 moles of SO3. There's my amount at equilibrium of the SO3. So if I bring this down here, that's my E for the SO3, 0.35. That is therefore increased by 0.35 moles. Remember, the C is my change line. So if that's increased by that quantity, the reactants will have decreased related to the ratios in the equation. So SO2 to SO3 is 2 to 2, it's 1 to 1. So therefore, the SO2 is decreased by the same amount, 0.35. The O2 has decreased in a 2 to 1 ratio, so that is decreased by half the amount. So the change is 0.35 divided by 2, which is 0.175. So therefore, at equilibrium, 0.425 to start minus 0.35 gives me at equilibrium 0.075 moles of SO2. And same here, 0.375 minus 0.175 gives me 0.2 moles. Okay, I've got my amounts at equilibrium now. X and P, mole fraction and partial pressure. So to get the mole fraction, I need to know how many moles of each gas I've got in relation to the total number of moles of these gases at equilibrium. So let's put to the side here, the total moles is 0.075 plus 0.2 plus 0.35, which is 0.625. That's my total number of moles in my system. So my mole fraction, my X, is going to be all of these divided by 0.625. Okay, and then the partial pressure is the mole fraction multiplied by the total pressure in the system. The total pressure was 2.5. So to get the partial pressure, I'm going to multiply all of these by 2.5. So that gives me then, for my P, the end is going to be 0.3. That's 0.075 over 0.65 times by 2.5. Same for this one, 0.2 over 6.25 times by 2.5. The partial pressure of oxygen is 0.8. And the partial pressure of the SO3 is 1.4. Okay, so I've now got my values that go into the expression. So if I bring that over here, Kp is now going to be equal to 1.4 squared, the partial pressure of the SO3 squared, over 0.3 squared multiplied by 0.8. So your final answer should come out at 27.2 to 3 significant figures. So marking for that one, as with any other calculation, the examiner will look first of all at the answer line. Correct answer, 5 marks. So breaking it down, if your answer is wrong, the marks for this one come from, first of all, working out the number of moles of the initial chemical. So both of these together is your first mark. Okay, your second mark is working out the amounts at equilibrium. So getting the 0.75 and the 0.2 is your second mark. Your third mark is the total number of moles. Your fourth mark is all the partial pressures together. And obviously the fifth mark is your final answer. So any errors earlier on obviously resulted in errors carried forward. So if you incorrectly worked out a number of moles here, but then did the process right, you would have got 4 marks. If you did that and then incorrectly worked out this one, but carried on correctly from there, you got 4 marks, and so on and so forth. So whilst not getting the right answer, you may still be able to get the majority of the marks, provided you follow the process.